Today we're going to talk about one of the important topics that we also need to discuss with momentum. So far we've discussed Newton's third law. For every action, there is an equal and opposite reaction. So the force of object A on B equals the negative force of object B on A. We've also discussed the impulse theory, where force times time is equal to the change in the momentum of an object. This last topic, conservation of momentum, takes these two concepts and puts them together. Let's think back to our lab. In the lab, we had two carts. We had one cart here and a second cart over here. They exploded away from each other because there was a spring plunger that acted on it. Looking at Newton's third law, we know that the amount of force the spring applied to cart A had to equal the amount of force cart A pushed on cart B. Therefore, it's pretty easy to see that carts A and B both had the same amount of force. We can also tell that this force acted for the same amount of time because the two carts were connected and separated. B couldn't be pushing on A when A wasn't pushing on B. So this was the same amount of time. Finally, that leads us into taking our impulse equation. Hopefully, by taking a look at these two statements, it's easy to see both carts had the same amount of change in momentum, but in opposite directions. Therefore, one had a positive change in momentum that was equal to the other one's negative change in momentum, because momentum, after all, is a vector. When we add these together, if we wanted to figure out the total momentum of the entire situation, they would end up canceling out. That's why we can see that the total amount of momentum would always remain the same even if a force acts between the two. This idea is called conservation of momentum. Conservation of momentum simply means that the momentum before something happens, the initial momentum, has to equal the total final momentum of an entire situation. So in this case, where we had two objects, we would look at the object one's momentum to start. So that would be object one's mass times its initial velocity. Add it to object 2's mass times its initial velocity, and that would equal, overall, object 1's mass times its final velocity plus object 2's mass times its final velocity. This would work if we had 2 objects, 3 objects, 4 objects. No matter what, if the forces are only acting on these objects and there's no outside forces created by anything, momentum will be conserved, and our total initial momentum will equal our total final momentum. There are 3 separate situations, and there will be 3 videos that follow that do a practice example for each. The first is explosions. That's similar to the lab, where we start with 0 momentum to begin with, a force creates something, and objects move. Then there's going to be an elastic collision, where 2 objects hit and bounce off, similar to billiard balls hitting each other. And the final would be an inelastic equation. And this would be the case where 2 objects hit and stick together. You will see these videos coming up.